What if the most sophisticated shelter engineering in all of human history happened in the one place on Earth where building was supposed to be impossible? Picture yourself standing on an open plain 20,000 years ago. Not a clearing at the edge of a forest, not a riverbank where driftwood collects. Just horizon, in every direction, as far as a human eye can see, nothing taller than knee height. The wind doesn't gust, it presses, constant and mechanical, like something alive that wants you gone. The temperature has crossed into the range where exposed skin fails in minutes. The ground beneath your feet is locked solid, meters deep, and has been that way for thousands of years. And somewhere in that landscape, a family is home. Not huddled, not dying, home. When archaeologists began uncovering evidence of how these people lived, the reaction among researchers wasn't admiration, it was confusion. Because what the evidence showed shouldn't have been possible. And understanding why it was possible changes something fundamental about how we think about human intelligence. Before we can understand what Ice Age humans built, we need to demolish the picture most of us carry of what the Ice Age actually looked like. The popular image is cinematic. Glaciers the size of mountain ranges, blizzards that never stop, a world buried under white and lifeless cold. That image is wrong in ways that matter. Yes, the ice sheets existed. At their maximum extent, glaciers covered nearly a third of Earth's land surface. But the inhabited zones of the Ice Age were not under those glaciers. They existed at the margins and beyond, a vast, wind-scoured, largely treeless landscape that scientists today call the Mammoth Steppe. The Mammoth Steppe was the largest terrestrial ecosystem in human history. At its peak, it stretched from the Atlantic coast of Western Europe, across the entirety of Eurasia, through Siberia, over the land bridge now submerged beneath the Bering Sea, and into the interior of North America. Cold desert grassland dry, swept by constant wind, carpeted in sedge and grass, but almost entirely devoid of trees. Why no trees? Several converging forces. Extreme cold compresses, growing seasons to the point where trees can't accumulate enough energy to establish themselves. Permafrost, ground frozen solid to depths of hundreds of meters, prevents the deep root systems trees require. Constant dry wind strips moisture from the soil surface. But the Mammoth Steppe was not barren. It was ecologically rich in ways we don't intuitively expect. It supported woolly mammoths, woolly rhinoceroses, cave lions, steppe bison, musk oxen, horses, reindeer, megafauna in densities that rival the Serengeti. For humans who could solve the shelter problem, this landscape offered remarkable abundance. And so the shelter problem became the central engineering challenge of the Pleistocene. Without wood, how do you stay warm? The first solution was not invented. It was discovered probably multiple times, independently, by humans in different parts of the world who all observed the same physical fact. The Earth is warm, not dramatically, not geothermally active, just consistently, reliably, measurably warmer than the air above it, once you go deep enough. At roughly 1 meter below the surface, something remarkable happens to temperature. The violent swings of the atmosphere summer heat, killing winter cold, essentially disappear. Ground temperature at that depth stabilizes. It doesn't fluctuate with the seasons. It doesn't drop with the wind. It holds, relatively constant, year-round. Modern geophysicists call this the zone of constant temperature. Ancient humans had no name for it, but they understood it completely in the most practical possible way. They dug down into it. Across Eastern Europe and the Russian plain, archaeologists have uncovered pit dwellings dating back 15,000 to 20,000 years. These are not random holes. The excavated profiles show deliberate planning, circular layouts that are structurally efficient, edges reinforced with packed sediment or stone, evidence of repeated occupation, implying the same family groups return to the same prepared sites, winter after winter. Experimental archaeologists, researchers who actually build these structures and live in them, have measured the thermal results. Even a shallow depression, just 40 to 60 centimeters deep, can reduce heat loss by more than 50% compared to a surface-level structure. In a world where the difference between warm and cold is the difference between alive and dead, cutting heat loss in half is not an engineering detail. It is the entire survival equation. Here is where Ice Age engineering begins to look less like survival improvisation and more like something else entirely. Modern building science understands that insulation works best in layers, different materials addressing different heat transfer mechanisms simultaneously. Conduction, convection, radiation. Each travels differently, responds to different countermeasures, requires different material properties to interrupt. This is taught in engineering programs as a relatively recent insight, refined over the 20th century as materials science matured. Pleistocene humans had already figured it out. The insulation systems archaeologists have reconstructed from Ice Age shelters are not single material solutions. They are layered composites, each layer targeting a specific mode of heat loss with a material precisely suited to interrupting it. Animal hides processed through labor-intensive stretching, scraping, and working created flexible outer walls that broke wind. This matters because wind doesn't just feel cold. Moving air strips the thin, warm layer that any insulated surface accumulates, dramatically accelerating heat loss through convection. A wind barrier is not comfort, it is structural thermal management. Beneath the hides, fur layers, often from multiple species with different fiber structures, created what physicists call still air pockets, tiny volumes of trapped, motionless air that conduct heat extremely poorly. The fur wasn't providing warmth directly, it was immobilizing air, because still air is one of the best natural insulators in existence, and it costs nothing except the knowledge of how to trap it. Between structural elements, grass, moss, and loose sediment served as filler insulation, bulky, low-density material, adding thermal mass and sealing gaps where convection would otherwise carry heat out. And layered over everything, sometimes literally, snow. Fresh snow is counterintuitive as an insulating material, but the physics are unambiguous. A typical snowpack contains between 80 and 95% air by volume air that is trapped, still, and thermally inert. Dense, settled snow approaches insulation values comparable to fiberglass bats used in modern residential construction. This is not metaphor. This is laboratory-measured thermal conductivity. Ice Age humans who packed snow against their shelter walls were not making do. They were applying a material whose insulation performance, gram for gram, rivals products sold in hardware stores today. If you want a single object that captures the full sophistication of Ice Age cold weather engineering, it is not the most ancient example. It is the most recent. The igloo. The word comes from Inuktitut igloo, meaning simply house. For a construction that Western observers historically dismissed as primitive, that plainness of name is almost ironic. An igloo is a compression dome. Every block cut from consolidated snow is shaped and angled to lean slightly inward as the structure rises. The geometry is not decorative, it is load-bearing calculus. As blocks press against each other, compressive forces distribute around the entire curved surface. The structure doesn't just resist collapse, it becomes stronger as snow accumulates on top of it. The weight of potential failure is redirected into structural integrity. Roman architects would have recognized the principle. Modern civil engineers would recognize it. The igloo arrived at the same solution from first principles, using a material that no engineering textbook from any civilization would have considered structural grade. But the interior design is where the igloo moves from clever to genuinely elegant. The entry tunnel is carved low, well below the level of the main floor. Cold air, which is denser than warm air, settles and drains into the tunnel. Warm air, which rises, accumulates in the domed interior above the sleeping platforms. Occupants sleep elevated above the cold air drainage zone and beneath the dome that collects their body heat. This is passive thermal stratification. No mechanical systems, no moving parts, no fuel required to maintain it. just the deliberate arrangement of space according to the physical behavior of air at different temperatures. It goes further. Body heat and a single small fat lamp cause interior snow surfaces to very slightly melt. This surface moisture migrates into the snow matrix and refreezes when temperatures drop gradually, developing a thin shell of solid ice on interior walls. This ice layer seals microgaps between blocks, eliminating cold air infiltration pathways, while simultaneously increasing structural rigidity and hardening the dome against wind deformation. The structure improves with occupation. Arctic expedition records document interior igloo temperatures ranging from -7 to +2 degrees Celsius, while outside air dropped below -40. That 40+ degree differential, maintained by body heat and a palm-sized lamp-burning rendered animal fat, represents insulation performance that many hastily constructed modern structures fail to match. Now set aside snow entirely, because some of the most astonishing shelter construction from the Ice Age used a structural material that had never been used that way before, and arguably has never been used that way since. In 1965, Soviet archaeologists excavating a site near the village of Mezherik, in what is now Ukraine, made a discovery that took years to fully interpret. Buried in Pleistocene sediment, they found the remains of 4 large circular structures, not built from logs, not built from stone, built from mammoth bones. Each dwelling used between 150 and 400 individual bones, assembled with evident structural logic. Mandibles, the curved lower jaw bones of mammoths, were stacked in interlocking rows to form foundation rings and lower walls. The slight outward curve of each mandible, when stacked in alternating orientations, created a scalloped structural wall that distributed load rather than concentrating it. Long limb bones, femurs, tibius, humeri served as vertical and diagonal support members. Skulls, the densest and most structurally robust skeletal element, were clustered at load-bearing points. Some tusks appear to have been arranged in arcing configurations that could have supported a hide roof frame. Mezherik dates to approximately 15,000 years ago. It is not the only site. Similar mammoth bone structures have been found at Kostenki, Mezin, and Udinovo, a geographic spread across the Ukrainian and Russian plain, suggesting this was not local improvisation, but a widely practiced architectural tradition. Think carefully about what this represents. In an environment with no timber, these builders surveyed their landscape and identified the structural properties of available materials with enough precision to select specific skeletal elements for specific structural roles. Compression members here, load distribution there, flexible attachment points at the apex. They were not scavenging shelter. They were reading a femur the way a structural engineer reads a steel I-beam. Not every solution required construction. Some of the most effective cold-weather shelter in the Ice Age world was not built, it was recognized. Rock outcroppings, cliff bases, river terraces with natural overhangs, low ridgelines that deflected prevailing wind, hillsides with southern exposures that accumulated solar heat in ways the open plain never could. Modern environmental measurements quantify the advantage. Blocking direct wind, even with an imperfect barrier, can reduce effective heat loss by the equivalent of raising ambient temperature by 10 to 15 degrees. A south-facing rock face in the northern hemisphere absorbs solar radiation preferentially and re-radiates it into the microclimate immediately in front of it, creating a thermal buffer that sits measurably warmer than the surrounding landscape, even on clear, bitter days. Archaeological analysis of cave and rock shelter sites across Europe and Asia has identified consistent patterns in how these spaces were used. Activity and sleeping areas cluster in elevated rear zones, away from cold air pooling near entrances. Stone arrangements near entry points show placements consistent with wind deflection. Ash deposits are positioned to maximize radiant heat distribution into occupied areas rather than toward exterior openings. These patterns are not random. Their consistency across sites, separated by thousands of miles and thousands of years, suggests a shared, transmitted understanding and inherited literacy for reading the thermal landscape. Before the first post was driven into frozen ground, the decision of where to build had already been made with precision that rivals modern site analysis. There is an assumption so deeply embedded in how we think about prehistoric survival that most people never examine it. The assumption is that survival in cold required large fire. It is intuitive. Fire is warm. More fire is warmer. The image of a roaring blaze at a cave entrance, holding back the dark and the cold, is one of the most persistent visuals in how modern people imagine prehistoric life. It is also, in crucial ways, wrong. Large fires consume oxygen at rates that require ventilation, and ventilation, meaning airflow through a shelter, is the single greatest driver of heat loss in any enclosed space. A fire that forces you to open your shelter to outside air defeats a significant portion of its own thermal purpose. The solution that Arctic cultures developed, and that archaeological evidence suggests was widespread, deep into prehistory, was counterintuitive. Less fire. Small lamps carved from soapstone or dense rock, burning rendered fat from marine or terrestrial animals, with wicks fashioned from moss or lichen. These produce steady, radiant heat without the oxygen demands of open combustion. They generated minimal smoke, enough to require a small ventilation opening, but not enough to require the wide gaps that a wood fire demands. This allowed shelters to remain nearly sealed. And in a nearly sealed shelter with good insulation, something surprising becomes possible. The metabolic heat output of 2 or 3 sleeping bodies can, on its own, maintain survivable interior temperatures in extreme cold. The fat lamp wasn't supplementing the fire. In the most sophisticated cold weather shelters, it was replacing it. This is the same principle that drives modern passive house design. Reduce loss before increasing production. Prehistoric survival was applying energy efficiency logic thousands of years before modern engineering gave it a name. Every technique we've described, the pit foundation, the layered insulation, the compression dome, the bone framework, the fat lamp shares a property that is easy to overlook because it doesn't appear directly in the archaeological record. It had to be taught. None of these techniques are intuitive. Selecting the right snow density for igloo blocks too soft and the dome sags, too dense, and the blocks fracture requires calibrated judgment developed over years of practice. Identifying which mammoth bones carry load and which fracture under stress is knowledge accumulated through failure, then success, then deliberate transmission. Understanding which hillside holds morning heat and which channels cold air downhill at night is the product of years of observation that someone then had to find a way to pass forward. Archaeological evidence for multi-generational site use is compelling. At many locations, excavation reveals not one occupation layer but several, separated by thin deposits of wind-blown sediment representing intervals of seasonal abandonment. The same site, used by the same cultural group, winter after winter, century after century. The shelter itself was not the technology. The knowledge of how to build the shelter, where to site it, how to orient it, how to construct and maintain it, when to abandon it, that knowledge was the technology. The shelter was merely its physical expression, and it had to be transmitted with enough fidelity to be rebuilt from scratch each season, in new snow, with whatever materials the current landscape provided, in conditions where errors in transmission could be immediately and lethally consequential. This is not primitive. This is one of the most demanding forms of knowledge management that exists. Embodied, practical, adaptive expertise maintained across generations under conditions of zero margin for error. Modern survival culture is obsessed with gear. The right knife, the right layering system, the right emergency bivouac. Browse any outdoor forum, walk into any outdoor retailer, and the implicit message is consistent. Survival is a problem of having the right objects. Ice Age survival was not about objects. It was about systems. Shelter selection was part of a larger seasonal strategy, coordinated across a social group, informed by multi-year knowledge of animal migration, snow conditions, prevailing winds, and site availability. The mammoth bone dwelling was not just a building, it was a node in an annual circuit. One stop in a deliberate seasonal cycle that moved people through a landscape the way a modern logistics network moves goods between distribution points. Evidence from multiple Ice Age sites suggests groups maintained networks of winter locations, places prepared, used, partially disassembled, and revisited across spans of time, exceeding the lifetime of any individual. The knowledge of where those places were, how to reach them, and what conditions made each one safe or dangerous represented strategic intelligence operating at landscape scale. These people were not reacting to winter. They were predicting it, deploying accumulated knowledge in advance of it, with a sophistication that, if described in the vocabulary of modern organizational theory, would be called adaptive, resilient, and operationally precise. Beginning in the mid-20th century and accelerating through the present, experimental archaeologists and wilderness survival researchers began systematically testing reconstructed prehistoric shelter designs under real conditions. The findings have been consistently humbling. Snow trenches, when properly sited and constructed according to principles appearing in multiple prehistoric traditions, reduce heat loss to the point where occupants can maintain core body temperature indefinitely in conditions that would be fatal in the open within hours. Debris huts, built with the layering logic seen in Ice Age archaeology, achieve insulation values that modern thermal calculation would predict not accidentally, but because the underlying physics was understood and deliberately applied. Mammoth bone structure reconstructions have confirmed the structural logic of the original designs. The interlocking mandible wall technique is not only functional, it is, for the available material, close to optimal. Again and again, experimental testing arrives at the same conclusion. What looks primitive is frequently optimized. The gap between prehistoric shelter and modern shelter is not a gap of intelligence, nor of engineering logic. It is a gap of material availability and margin for error. Modern buildings can tolerate imprecision because we have redundant heating systems, emergency infrastructure, and insulating materials with extraordinary performance. Mistakes get caught before they become fatal. Ice Age shelters had none of those margins. They had to be right, every time, and the evidence suggests they were. So here is what 20,000 years of distance has allowed us to finally see clearly. Human survival was never, at any point in its history, about having ideal materials. It was about understanding the system you were embedded in. Ice Age people on the Mammoth Steppe did not look at snow and see an obstacle. They saw an insulating medium with specific, exploitable thermal properties. They did not look at a mammoth skeleton and see a carcass. They saw a structural material with differentiated load-bearing characteristics across its components. They did not look at wind and see weather. They saw convective heat transfer, a fluid dynamic they could interrupt, redirect, or exploit depending on context. They were not simply enduring the Ice Age. They were studying it. Every winter was data. Every shelter failure was a lesson. Every successful survival was information added to a body of transmitted knowledge, refined across generations, with the care we now reserve for engineering documentation. These were not desperate people making do in the dark. They were the engineers of an age we have barely begun to understand, practitioners of a detailed, functional, field-tested science of thermodynamics and structural mechanics that predates every civilization we typically credit with those ideas by tens of thousands of years. The technology was real, it worked, and the people who built it were not primitive. They were the first engineers, and the cold was their laboratory. If this reframes how you see the people who survived the Ice Age, if it makes them feel more intelligent, more deliberate, more recognizably capable than the word prehistoric usually implies, that is exactly what the archaeology is showing us. Site by site, shelter by shelter, thermal measurement by thermal measurement. The deeper we look into prehistory, the less primitive it appears. Subscribe to Prehistoric Shadows, where we excavate the forgotten science and quiet engineering that allowed our species to endure the most hostile chapters of its existence. Because the real story of human survival in the cold is not a story about luck or brute strength or even fire. It is a story about thinking, and it starts far earlier than you ever imagined.